All right, video for lesson 8.6, Binomial Theorem. So the two learning targets, we need to determine how to find what are called binomial coefficients. And ultimately that's going to lead to this, which is the most important learning target for this lesson, expanding a binomial. So a binomial, really binomial means two terms. It's an expression of the form a plus b. It has two terms. And expanding a binomial means we take a binomial and raise it to a certain power, like a plus b squared or a plus b to the fourth. So on a small scale, you can see here I've written some of the expansions. A plus b to the first power obviously is a plus b squared is a squared plus 2ab plus b squared. Now keep in mind, a plus b squared, we're not just distributing exponents. That's not how this works. Remember, raising a binomial to a power means a plus b times a plus b. And similarly, a plus b cubed means a plus b times a plus b times a plus b. Distributing it all together by hand and expanding it out into a polynomial expression like that. So you can imagine by hand, this takes quite a bit of time. And as the powers increase, a plus b to the fifth, a plus b to the 20th, this could be a very tedious thing to do by simply multiplying binomials together using the distributive property. So lucky there's something called the binomial theorem and finding binomial coefficients, which helps make the process a little quicker. So first of all, what can be generalized though? What patterns can we start to see emerging here? And one of them is there's always one more term than the power it's being raised to. That's what this number one here, n plus one terms. For example, a plus b squared, you can see it here, has three terms. N being the exponent. If the exponent is 2, then there's n plus 1 terms. So if the exponent is 2, then there's 3 terms. And you can see that the first term of the expansion is always the first term of the binomial raised to the same n power. And then the last term of the expansion is always the last term of the binomial raised to the power of n. That's what it is talking about here in this first thing. Now the second one, perhaps you've noticed powers of a, for example. We start with, in this case, let's look at a cubed here. The next power of a is a squared, and then the next power of a is a to the first power. And then you could say there is no power of a here, really. It's a to the 0 power, which is just 1. So the powers of a are decreasing by 1. The powers of b, here it's b to the first power, here we have b to the second power, and here we have b to the third power. So the powers of b seem to be increasing by 1, and we can look here at a plus b to the fourth to see if the pattern holds. We have a to the fourth, and then we have an a cubed, and then an a squared, and then a to the first power. And similarly, the powers of b are increasing, b to the first, b squared, b to the third, b to the fourth. So the powers of that first part of the binomial are increasing, or decreasing rather, and the powers of the second piece of the binomial are decreasing. Now, another generalization we can make here is in regards to the sum of the exponents of each term. Looking at this term, for example, we have a cubed times b to the first power. If we sum the exponents, 3 plus 1, it's a total of 4, which is the value of n. And that would be true of any term. If we look over here to this term, we have a squared times b squared. The sum of those two exponents is 4. Or here with this term, we have a to the first power times b to the third power. The sum of those would be 4. So for any given term, the sum of the powers is equal to n, the power originally that the binomial is being raised to. And these generalizations are helpful to make a shortcut for expanding binomial. So that addresses what's happening with the variables a and b. What hasn't been addressed are the coefficients of each term. For example, a plus b to the third power, we have a coefficient of 1, really right here, then a coefficient of 3, and then a coefficient of 3, and then a coefficient of 1. With a plus b to the fourth power, we have a coefficient of 1, a coefficient of 4, then 6, then 4, and then 1. So we need to start to discover some generalizations or a pattern or a rule for determining those coefficients, because those are important pieces of the expansion. So if we were to look now at a plus b to the fifth power, if we followed these generalizations here, we could determine the terms of the expansion like this, but what we wouldn't know are the coefficients that would go in front of those terms. So real quick before we get to those are called the binomial coefficients. Let's just use the knowledge we have of those three generalizations to write the 6 terms. And I say there are 6 terms because remember, one of the generalizations, there's always one more term than the power that's being raised to. So we can write at least the terms without the coefficient. So the first term is going to be a to the fifth, and there's going to be a coefficient in front of that one. The second term, there's going to be a coefficient. Remember, we decrease the power of a, and then b is going to be raised to the first power because the sum of the exponents has got to equal that original exponent there. And then we have another term with a coefficient, and then we decrease the power of a and increase the power of b. Another coefficient, this is going to be a squared b cubed. So another coefficient, excuse me, times a to the first power times b to the fourth, plus the final term there, we have a coefficient times b to the fifth. I'll just count the number of terms we have. 1, 2, 3, 4, 5, 6 terms. But we need to figure out then, what are these coefficients going to be? So, like I said, those are called binomial coefficients. There's a few pieces of information or some new vocab that we need to learn before we go full-blown binomial coefficients. One of them is a mathematical notation here, which is known as n factorial. So this exclamation mark is a mathematical operation called factorial. And what it means is you're multiplying all the positive integers up to that value of n, all the way down to 1. So for example, if it's 5 factorial, it's multiplication of all the positive integers from 5 all the way down to 1. So it's 1 times 2 times 3 times 4 times 5. That's what 5 factorial means. Or 10 factorial would be 1 times 2 times 3 times 4 all the way up to times 9 times 10. And then by definition, 0 factorial is equal to 1. Now here's the definition we're going to use for the moment, at least, for binomial coefficients. We're going to let n and r be non-negative integers. Non-negative means positive, integers means whole numbers. R has got to be less than or equal to n. The notation we're going to use for binomial coefficients is this. It's n on the top, r on the bottom, in a set of parentheses. And that's mathematical notation for this operation right here. N factorial divided by r factorial multiplied by n minus r factorial, where n is the original power that the binomial is being raised to. So looking back at the example we are working on, a plus b to the 5th power, there's going to be 6 terms, which we already found. We didn't have the coefficients, and they're going to have the following coefficients. The coefficient of the first term, notice that the top value n stays the same because we're raising that binomial to a power of 5. The bottom value starts at 0 and increases for each subsequent term all the way up to right there, where we have 5 it's not a numerator, 5 in the top and 5 in the bottom of that operation. Now, how this is read out loud, this, for example, just by way of notation, if you hear this in conversation, mathematical conversation at least, the way you would read this out loud is 5 choose 5. That's the verbal for that notation. This one here would be 5 choose 4. This one here would be 5 choose 3, is how that's read out loud. So what we need to do then is perform the mathematical operations for all of those coefficients. So starting with the top one here, 5 choose 0, we use this formula here, where this is n, the top value is n, and the bottom value there is r. So it's 5 factorial divided by 0 factorial times 5 minus 0 factorial. Now remember, 0 factorial was given a value of 1 by definition. And then 5 factorial divided by 5 factorial are both going to be 5 times 4 times 3 times 2 times 1, which is going to cancel each other out. So it's 1 divided by 1, which is 1. So 5 choose 0 is equal to 1. So this first coefficient here is 1. Now moving on to 5 choose 1, you can see the numerator here is 5 factorial, which is 5 times 4 times 3 times 2 times 1. And then we have 1 factorial, and then 5 minus 1 factorial is just 4 factorial, which you can see is written right here. And then the 5, or the 4 and the 3 and the 2 and the 1 factors are going to cancel out. So we have 5 divided by 1, which is 5. So 5 choose 1, the coefficient up here is going to be 5. Now 5 choose 2, again the numerator is 5 factorial, 5 times 4 times 3 times 2 times 1. Then we're going to have 2 factorial, which I've written here. And then 5 minus 2 is 3, so 3 factorial, which I've written there. So we get the 3's and the 2's and the 1's cancel. So we have 5 times 4 divided by 2 times 1 is 2. 20 divided by 2 is 10. So that's the coefficient here, 5 choose 2, which is 10. 5 choose 3, you can see here the 2's and the 1's would cancel, and then we have a 3 here that can cancel. So we have 5 times 4 divided by 2, which is also 10. So 5 choose 3, that coefficient up here, is also 10. We got 5 choose 4. So we have 4 factorial, which is 4 times 3 times 2 times 1, multiplied by 5 minus 4, which is 1 factorial, which is here. And then the 4s, 3s, 2s, the 1s, so it's 5 divided by 1, which is 5. So 5 choose 4, which is here. That coefficient turns out to be 5. And finally, 5 choose 5. So we have 5 factorial divided by this 5 factorial, which just means the 5s and the 4s, 3s, 2s, the 1s are going to cancel. And then it's 5 minus 5, which is 0 factorial. Remember, by definition, that's 1 factorial. So it's 1 divided by 1, which is 1. So 5 choose 5, finally right here, that coefficient is 1. So a plus b raised to the 5th power with the correct coefficients and the correct expansion is there. So it isn't necessarily a quick process, but I believe it is faster than having 5 binomials written out multiplied together that you would have to multiply using the distributive property like this. That would be a much more tedious task. Now, this isn't meant to be done with simply A and B. Those are placeholders. A and B are going to be replaced with a variety of values, like 2x plus 3 to the 5th power, for example, where we treat 2x as A and 3 as B. And we do the same thing, but the nice part about it is it's being raised to the 5th power, and so we're going to have the same exact coefficients here that we just figured out, because we would figure them out using the same binomial coefficient theorem of 5 choose 0, 5 choose 1, 5 choose 10, or 5 choose 2 rather. So they're going to have the same coefficients, but rather than having a to the 4th and b to the 1st, or a cubed and b to the 2nd, we're going to have powers of 2x and powers of 3. So if we wanted to compare what we're going to expand here to what we've expanded here, for the first term the coefficient is 1. So we have 1 times, and then a to the 5th just represents the first term raised to the 5th power. And now we move on to the second term. Comparing it to this, it looks like it has a coefficient of 5. And then the first term, in this case 2x, is raised to the 4th power. And then the other term, which in this case is 3, is raised to the 1st power. This is synonymous to 5 times a to the 4th times b. Here we have 5 times a to the 4th times b. Now we move on to the third term, which has a coefficient of 10. So 10, and then the a term, which is the first term there, is raised to the 3rd power. So we have 2x raised to the 3rd, and then we increase that power. And the 4th term here looks like it has another coefficient of 10, and then our first term a, or 2x rather, decreases by a power. Our second term 3 increases by 1. Next term has a coefficient of 5, then 2x is raised to the 1st power, 3 is raised to the 4th power, and finally for the last term we have a coefficient of 1, and then 3 is raised to the 5th power. And then we go through and simplify. First term, 2x to the 5th power. 2 to the 5th power is 32, and x to the 5th power is just x to the 5th power. Now we have a lot of multiplying to keep track of here. First of all, 2 to the 4th power is 16. And then we have 16 times 5, and then that 16 times 5 is also going to be multiplied by 3. So we have a lot of multiplication there to keep track of. So 2 to the 4th, like I said, is 16. 16 times 5 is 80. And then 80 times 3 is 240. So we have 240. And the variable is going to be right here, x to the 4th. Okay, now to this term, we are going to have 2 now raised to the 3rd power here, which is 8. And then 8 times 10 is 80. And then 80 times 3 squared is 9. 80 times 9 is 720. And then the variable is going to be x cubed. And moving on to here, we have 2 squared there, that's just 4. 4 times 10 is 40. And then 3 cubed is 27. So we have 27 times 40, which is 1080. And then it's going to be x squared. Now moving over here, we have 2x raised to the 1st power, which is 2x. And then 2 times 5 is 10. 3 to the 4th power is 81. 81 times 10 is 810. And the variable is going to be x. And finally, last term there, 3 to the 5th power is 243. So this is what it's actually going to look like when you're practicing expanding a binomial. You're going to need to know the patterns where, like I said, the exponents are decreasing by 1 or increasing by 1. So you're going to need to remember those patterns. Also that whatever power you're raising it to, there's one more term than that power. So if we're raising to the 5th power, it's got to be 6 terms. 1, 2, 3, 4, 5, 6. And then being able to find initially the coefficients of each expansion term. So we had 1, 5, 10, 10, 5, and 1. We have found those, or we had found those, using binomial coefficient, which is these theorems up here. 5 choose 0, 5 choose 1, etc. Now, for an easier way, at least for finding the binomial coefficients, it's called Pascal's triangle. And when I say easier way, it's kind of a double-edged sword. It supposedly could be easier for small values of n if you're raising a binomial to a large power of n, like 15 or 25. Pascal's triangle may not be quite as easy as using the binomial theorem with the binomial coefficients. But we're generally going to be limiting our expansions to relatively smaller powers of n. So you may find that using Pascal's triangle is a quicker way of finding the coefficients. So here's Pascal's triangle. You notice that each row always starts with a 1. The first entry in each row there is a 1. Okay? And the pattern here is every term after the 1, oh, and it always ends with a 1 as well, sorry. So we have the row ending in a 1. So it begins and ends with 1s. The terms in the middle, this, for example, are found by adding the two terms directly above. So 1 plus 1 gives us 2. This 3 right here, for example, you add the two terms above it. 1 plus 2 gives us a 3. Same thing here, this 2 and this 1. Or here, with this 4, we add the 1 and the 3. For the 6, we get it from the 3 and the 3, the 1 and the 3. Now each row is corresponding to its particular power of n. Top row being, if you were to raise a binomial to the power of 0, then there is only going to be one coefficient, because a plus b to the 0 power is equal to 1. Anything raised to the 0 power is 1. That's where that top row comes from. If we're raising it to the first power, a plus b to the first power is just a plus b with both coefficients of 1. That's where the second row comes from. And so on and so on. So if you're raising something to the fourth power, for example, where n equals 4, it's actually the fifth row of Pascal's triangle. 1, 2, 3, 4, 5. So that is something to keep in mind. So if we wanted to look at the last example we did, where it was raised to the fifth power, n equals 5, we would need to complete one more row of Pascal's triangle. Remember, it always starts with a 1. And then we have 1 plus 4, so that'd be 5. And then we would have a 4 plus 6, that's 10. And we'd have a 6 and a 4, it's another 10. And then we'd have a 4 and a 1, which is 5. And then it ends in a 5. So that row of Pascal's triangle gives us the exact same coefficients as that binomial coefficient formula that we were using earlier. And I think, well, this is way easier. And yes, it can be easier, like I said, for smaller values of n. The one drawback is it's similar to a recursive formula, where if you wanted the fifth row, or rather this is the sixth row when n equals 5, you have to complete all the rows above it in order to get that fifth row. If I wanted the 10th row, I'd have to complete all 9 rows. If you wanted the 40th power, you'd have to complete 41 rows. So using Pascal's triangle is easier, I would say, for relatively small values of n, where you wouldn't have to make a large portion of the triangle in order to figure out the coefficients. So as an example, using Pascal's triangle, let's expand x plus 2y to the fourth power. We're going to remember this, you can think of as our a term, this we can think of as our b term. And if we're raising it to the fourth power, we're going to want the row of Pascal's triangle that corresponds to n equals 4, right here. So these are going to be our coefficients. So we're going to start with a coefficient of 1, and then we take the first term and raise it to that power. So it's times x to the fourth. Now the second term is going to have a coefficient of 4, and we decrease the power of that term by 1. And now we incorporate that term to the first power. And now the third term is going to have 6 as a coefficient. We decrease that power by 1. We increase that term's power by 1. And we move on to have a coefficient of 4. This term is going to decrease to a power of 1. This term here is going to increase to a power of 3. And finally, we have a coefficient of 1. And then this last term is going to be raised to the fourth power. Okay, and then we go through and simplify each term. 1 times x to the fourth is simply x to the fourth. This term, we're going to have 2y to the first power, which is 2y, and then the 2 is going to multiply with the 4 to make 8. So it's 8x cubed times y. Here we're going to have a 2y to the second power, which is 4y squared. The 2's are going to be squared, and then y is going to be squared. So we're going to have 4y squared, and then the 4 and the 6 are going to multiply to give us 24. So 24x squared y squared. Then here, this term, 2y to the third power, the 2 is going to be cubed and the y is going to be cubed. So 2 cubed is 8. 8 times 4 is 32. X y cubed. And then we're going to have 1 times 2y raised to the fourth, which is 16y to the fourth. Let's take a look at another example here. And now we have two terms are subtracting. Doesn't make it any more difficult. You just need to pay closer attention to your minus signs and your plus signs with this one. So it's being raised to the third power. So we would need 4 rows of Pascal's triangle. So these are going to be our coefficients, 1, 3, 3, 1. The first term is going to have a coefficient of 1, and then it's going to be the first term of the binomial raised to the power of n, in this case, 3. Now moving on to the next term, it's going to have a coefficient of 3, and then our term of 4x is raised to the second power, and then the second term is negative 3, so negative 3 is going to be raised to the first power. The next term also has a coefficient of 3. The 4x is raised to the first power, but now the negative 3 is raised to the second power. Finally, the last term has a coefficient of 1, and then it's the last term now that's raised to the power of n, which is negative 3 to the third power. Let me simplify. 4x raised to the third power, 4 cubed is 64, and then x cubed is x cubed. And actually I'm going to hold off on writing a plus sign just to verify, because now we have negative 3 to the first power, which is negative 3. Here we have 4 squared, which is 16. And that's also going to be multiplied by 3. So 16 times 3 is 48, and then 48 times negative 3 is negative 144. So we're going to have minus 144 x squared. Moving on to this term here, we're going to have a negative 3, but it's raised to the second power, so that's 9. And then 9 times 4 is 36. And then 36 times 3 is positive 108, so we have 108x. Finally, last term here, and again, I shouldn't have started with the plus. Apologies. Always want to verify. We've got negative 3 raised to the third power, which is negative 27, so I'm going to do minus 27. So take a moment, pause the video, and I want you to try this one on your own, or attempt it, see what you can do. 2u minus 3v to the fourth power. All right, let's take a look. Raising it to the fourth power means we need 5 rows of Pascal's triangle. So those are going to be our coefficients there. And then we have the term that can act as A, and then a term that can act as B. So the first term has a coefficient of 1, and then it's 2u to the fourth. Then we have a coefficient of 4, and then 2u is raised to the third power, and negative 3v is raised to the first power. And we have 6 2u squared and negative 3v squared. Then we have a coefficient of 4 with 2u to the first power and negative 3v to the third power. Finally, last term, coefficient of 1, negative 3v to the fourth. And we simplify. So, first term, coming back here, 2u raised to the fourth power is 16u to the fourth. And we have a negative 3v to the first, which stays negative 3v. Here we have a 2 cubed, which is 8. 8 times 4 is 32, and then 32 times negative 3 is negative 96, and we're going to have a u cubed and a v to the first power. Okay, now the next term here, we've got negative 3, but it's raised to the second power, so that's 9. Here we've got a 2 squared, that's 4. 4 times this 6 here is 24, and then we have 24 times 9, which is positive 216. We're going to have u squared and times v squared. Okay, moving on to here, we're going to have a negative 3 cubed, which is negative 27. And then we have 2u, but that's raised to the first, that stays a 2. 2 times 4 is 8, so we need 8 times negative 27, which is negative 216. So minus 216, we're going to have a u to the first power and a v to the third power. And finally there, that last term, negative 3v raised to the fourth power. Negative 3 to the fourth power is positive 81. And that's going to be multiplied by v to the fourth power. So that would be the expansion of that binomial right there. So that is really the main part of lesson 8.6, is being able to expand a binomial. And I would imagine most students would choose to use Pascal's triangle to find the coefficients of each binomial term, or each term of the expansion, which is fine. There is one little spin-off topic here that I guess is considered part of expanding a binomial, but sometimes it's helpful to isolate just a single particular term rather than looking at an entire expansion. So if we said, what is the 10th term in the expansion a plus b to the 14th? Rather than trying to write out the whole expansion and then trying to count over to the 10th term, we can just find the 10th term in isolation of the rest of the expansion. And we are going to do this using the binomial coefficient formula rather than trying to use Pascal's triangle, because like I said, for the 14th exponent, or to the 14th power, we would need 15 rows of Pascal's triangle. So the binomial coefficient for the 10th term is going to be 14, choose 10. So the formula said that's 14 factorial divided by 10 factorial times n minus r, which is 14 minus 10, so that's 4 factorial. Now, you might get to a point where you don't need to write this all out, but just to illustrate it, this 14 factorial, remember, is 14 times 13 times 12 is 11 times 10. Give us a little more room here. Okay, and then 10 factorial and then multiply by another 4 factorial. So the 10 all the way down to 1. So the 10 times 9 times 8 times, and this 10 times 9 times 8 is going to cancel out. So really it's 14 times 13 times 12 times 11 over 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. So the denominator is 24. The numerator is 14 times 13 times 12 times 11, which is 24,024. And then 24 divided by 24 is 1,001. So the 10th term in the expansion is going to have a coefficient of 1,001. And then the 10th term, as far as the variables, we know it's going to be a combination of a to a power and b to a power. So a and b. And remember, the exponents of those have to add to 14. Now, isolating a, for example, if this is the 10th term, there are going to be 9 terms in front of it, all with powers of a greater than this power that we're looking at. So the 9 terms in front of it means, one simple way to think about this, we could subtract 9 from the original power, which was 14. So for the 10th term, a would have a power of 5, 14. Subtract the 9 terms that would have come in front of it. And then if the 2 powers have to add to 14, then b has to have a power of 9. So the 10th term in the expansion is 1001, a to the 5th, b to the 9th. And that brings us to the end of lesson 8.6. So just to review, really the most critical topic here is being able to find the entire expansion of a binomial. And there were those 3 generalizations where the exponents of the first term are decreasing with each subsequent term. The exponents of the second term are increasing with each subsequent term. The sum of the exponents in each term need to add together to the original exponent. Finding the coefficients, a quicker way may be to use Pascal's triangle. So make sure that you notice how to find and use Pascal's triangle. There aren't many homework problems to do from lesson 8.6 because they can be a little time consuming. So I think I only assigned 5 or 6. Make sure you get enough practice in. And then as a little side note, we practiced finding just a term in isolation of the entire expansion. If you want to find just one particular term, it may not be wise to use Pascal's triangle. You can find the coefficient using the binomial coefficient formula.